Now we're looking at the definition of local maximum and minimum values. They're going to be similar to the definition of absolute. If you want to be a local maximum, your y value needs to be larger than y values in an interval. Now, it needs to be in an interval, so it doesn't need to be across the entire domain. That's the difference between absolute and local. Local also are called relative extrema. So it can be a local or relative extrema. Same thing for the minima. It's just that y value needs to be less than all other y values on an interval. Then it's a local minimum. So, taking a look at this graph right here, the differences between absolute and local extrema should be apparent. This is a closed interval, so it's guaranteed to have an absolute max and an absolute min. We'll locate those first. I have an absolute maximum at S, and I have an absolute minimum at B. That's the highest y value that my graph ever achieves, and this is the lowest y value that the graph ever achieves. Now I can have more than one local extrema. If it's an absolute extrema, it's sometimes a local extrema. Since local extremas have to be in an interval, they have to be on interior points, so they can't occur at endpoints. So endpoints could never be local. So this point right here is nothing significant. It's not, this point right here is nothing. It's not a local minimum. It's not an absolute minimum. It's an exterior point. It's the end point of the interval. This point at point P is a local minimum because in an interval around it, just means some bubble around it, it is the lowest point. There's no smaller value of f nearby. If I look at the point at Q, again, it is the highest point in an interval. There's no greater value of f nearby, so it's a local maximum. And then I have another local minimum at R. There's no smaller value of y nearby, or f of x nearby. When I get to the next point, it was a local maximum, but is also, sorry, it wasn't absolute maximum, I meant to say. It was also a local maximum because it is an interior point and there are no other y values high nearby. So this one is both a local min and an absolute, a local maximum and an absolute maximum. When I get down to my absolute minimum, this is not an interior point, so it is not a local minimum. Because is that an endpoint? It is not local. Okay, just absolute. Okay, note number 1, when is an absolute maximum or minimum extrema also relative? If it is at an interior point. So if an absolute extrema is at an interior point, it is also local. Okay, let's look at the next page. Example 3, verify that the points given are relative extrema for the following functions, then find the derivative at those points. Okay, so the first point appears to be a local minimum because it is the smallest point in its bubble. So it does look like it is a relative local minimum. Then it says find the derivative at those points. So let's do that. Using our shortcut rules, f prime of x, the derivative of x is 1. I'm going to rewrite f above it real quick. F of x is x plus 27 times x to the, 27 halves. I didn't notice that 2 in the bottom at first. 27 halves times x to the negative 2 power. So when we take the derivative we'll have plus 27 halves times negative 2 x to the negative 3 power. So that simplifies to 1 minus 27 x to the negative 3. Okay. I want to find the derivative at that point. So next I want to evaluate f prime at 3 specifically, since 3 is the x-coordinate of that point. So I have 1 minus 27. I'm going to write the x to the negative third as x cubed in the denominator, so over 3 cubed. So that's 1 minus 27 over 27. 1 minus 1, so it's 0. Okay. So the tangent to this would be horizontal. There's a slope of 0 at that point. Not surprising, hopefully, that our slope should be 0 at an extrema. We used slope equals 0 before to identify where we might have extrema. Let's take a look at the next one. This next point right here seems to be another local minima. So let's find its derivative and evaluate it. So the derivative of this function, if I use the chain rule, pull the power down, 2/3 times the inside, x plus 2, to the 2/3 minus 1, which is negative 1/3, times the derivative of the inside, chain ruling that, and the derivative of the inside is 1. Now I want to evaluate that at negative 2. So I have 2/3 times negative 2 plus 2 to the negative 1/3. That's 2/3 times 0 to the negative 1/3. Now usually when you raise 0 to any power, it's 0. However, that power is negative. That's the same thing as 2 over 0 to the 1/3 power times that 3 in the bottom. And because that 0 is in the bottom, this is undefined. Now, if a line that has slope 0 is horizontal, a line that has a slope that is undefined is going to be vertical. So it means that we have a vertical tangent here instead of a horizontal tangent. And you can see that that appears to be true, that we have a vertical tangent at this point. Okay. In the previous chapters, we were focusing on identifying where derivatives were equal to 0 to identify extrema. But we don't want to lose that we could also have the undefined, the vertical tangent. We could also have an extrema. So what can we say about the derivative of a function at a relative extrema? It looks like we have two possibilities. The derivative may be equal to 0 at the extrema, or the derivative may fail to exist. So the derivative f prime of c may be equal to 0, or the derivative f prime of c may, since this is undefined, it doesn't exist. So we can say it does not exist at c. If c f of c is a relative extrema. That leads us to the local extreme value theorem. The extreme value theorem says that if f has a local maximum or local minimum value at c, then the derivative, if the derivative exists, then the derivative is equal to 0. The derivative may not exist, in which case it may be undefined, but the extreme values theorem says that if it has a derivative that does exist, that derivative is 0. Now, to be able to figure out where the extreme values exist, we're going to have to look for what are called first order critical values. First order critical values need to be interior points where the derivative is either equal to 0 or where the derivative does not exist. These are going to be candidates for extrema. Hold on a second. candidates for Extrema. We call these first order because they're where the first derivative is equal to 0 or doesn't exist. We will later talk about second order critical values. In the textbook in my math lab, they're just called critical points, which can be a little misleading because they use the same term for the second order ones, which is if the second derivative fails to exist or equals 0. So we're going to be a little more explicit there. These are our first order critical values. These are points that we must locate in order to find the maxima or minima analytically instead of looking at a graph. And x equals c must be in the domain of f in order to be a first order critical value. So it's not in the domain even if it meets the criteria that the first order doesn't exist or it's not equal to 0. If it's not in the domain, because the domain of the derivative has to be a subset of the domain of the original, it's not going to count. Okay, so if I look at the picture at the bottom of the page here, this is a picture of a case where the first derivative doesn't exist. The first derivative does not exist, but this point right here is not going to be a critical value because you are not continuous. Okay, so x equals c is not a critical value. And with a local maximum at c where the derivative does not exist, this is another case where my derivative does not exist. This one is a critical value and it is going to be an absolute extrema.